Well, more noise with recording. Okay, so hello everyone. It's my pleasure to introduce Viet Andrin. He's currently a PhD student in the Speech Lab Graduate Center in CUNY, New York University, under Professor Michael Mandel. And so Viet has also been before 2 times interning at Amazon. He also worked before at Texas Instruments. And today he will talk about unsupervised and semi-supervised speech enhancement. So with that, the floor is yours.
Yeah. So thank you, Sebastian, for the introduction. So today I would like to talk about the topic unsupervised and semi-supervised speech enhancement. My name is Việt Anh, and my mentor is Sebastian from the Audio and Acoustic Research Group. First of all, I would like to thank you, Sebastian, and the Audio Acoustic Research Group to let me work on the really interesting project and the cooperation from the other team. So let me first start by discussing the problem of speech enhancement. So the speech enhancement problem is that we want to removing noise and reverberation while maintaining speech quality. For example, let me play a noisy input here. Can you hear it? Yeah. So you can see the spectrogram here. With one axis is time and another axis is frequency. And you can see that a lot of spectrogram are covered by noise here. So here is the clean speech. Let me play again. I think it's noisy.
Footsteps through wild adventures down to the fountain in the stable yard, and even beyond, where paddocks were and the berry patches.
Yeah, so you can see that on clean speech, the spectrogram is very clear. So you can see some speech signal here in the red color or yellow color. Then you can see some pattern here. So for speech enhancement, the input will be a noisy spectrogram like that, or a time domain signal. Because some speech enhancement, they work on the time signal input and some work on spectrogram input. And then what we want is output is a clean spectrogram here. So let me describe why we need speech enhancement. So for human, we want to improve listening comfort because we want to remove all the background noise. For example, like if we have a meeting and maybe there's some construction outside, or there are fans noise or a lot of noise outside. It also can do to improve intelligibility for hearing impaired person, or to remove disturbing background noise. And for machine, it can help to remove unnecessary signal so that the machine can use the most important signal, and then from that it can improve the overall recognition performance. Many applications, for example, from human to human communication, we can have right now is really a lot of people using, for example, video conferencing product like Microsoft Teams and Zoom. So because we have a lot of people meeting together, so if there are unwanted background sound from one side can affect the meeting. So that's why we want to remove it. Also, there is application in mobile phone or hearing aids. Addition to human communication, it can use to be a pre-processing for machine application. For example, for speech recognition. For example, like in Microsoft Teams, after the meeting, we have meeting transcription, and then the speech enhancement can be like a pre-processing step before we put it to other further processing. It can also help with speaker recognition or emotion recognition, and there are many more, but I don't have a chance to describe everything in here. So what is the current problems in speech enhancement? So most of speech enhancement training datasets are synthetic now. So what we do is that we try to mixing clean speech. So we have a data set, clean speech data set, maybe we record in studio with very high quality, professional audio equipment. And then we have separate noisy corpora. So for example, we record some street noise or noise on the coffee shop. Yeah, a lot of noise. And then we mix them together. So some of the problem is we know that the studio quality training data is expensive because we need to record a lot of people talking a variety of topics. We need room equipment. Also, it's very hard to synthetic every acoustic condition that happen in real world. So that's why there are domain mismatch between synthetics and then real world noisy speak or audio. So for example, if we want to remove noise on team, there are a lot of background noise happen that we don't have it on the recording, or the noise condition, acoustic condition is different because different meeting have different acoustic condition. Another problem is that the speech enhancement system remove noise, but because they try to remove noise, so sometimes they are speak in there, so like maybe in a high frequency point, they are both speak and noise. So when you remove too much noise, then maybe the speech signal is distorts. So that's why it leads to the problem of when you improve the speech enhancement, then the ASR performance is degradation. So it's so famous that even in the Google Cloud website, they mentioned that, however, applying noise reduction signal processing to the audio before sending it to the service typically reduce recognition accuracy. So it means that for team meeting, if we want to make the human noise, a human feel more comfortable with the speech, we should sacrifice the machine ASR. So that is a problem. So how we can solve it? So that's why we have some motivation and goal for the project. The first one is that we want to utilize abundant real-world noisy recording for speech enhancement, because that the conventional method, they have the input is synthetic noisy with clean speech and noise, and the target is clean speech. So that's why we need clean speech. But how we can utilize abundant noisy recording in here? So that's why we need to move to unsupervised method. For example, we don't use clean speak as target anymore. We can use the real world noisy recordings as a target. The second thing is that because the current real-time deep learning speech enhancement system often degrade ASR performance. So that's why we try to work on the project and then set some goals. The first goal is, of course, we want to improve the perceptual quality of enhanced speech. So yeah, it try to improve speech. The second thing is that we try to utilize abundant real-world noisy recording and using the big data set instead of the small clean data set that we have. The third one, we want to mitigate the ASR performance degradation problem when we're using speech enhancement. So we want to remove the trade-off between the speech recognition and speech enhancement. The next will be the related work. So in here, we describe one current state of the art for unsupervised speech enhancement. So on the top figure, you can see here, it's a supervised permutation invariant training. And then the below figures is the unsupervised one. So in a supervised method, they require the clean speech here, for example. So this signal is only single signal. While in the second one, the unsupervised, the input not a clean speech anymore, but it can be a mixture here. So you can see the red one and then the brown one here. So it is two signals mixing together, or it's a noisy recording that already has inside the speech and a signal. So from this one, they try to propose a reconstruction loss, so that when they output all the source here, they summarize to the input picture, and then they have some kind of construction loss. Yeah, so that's why they can do it in unsupervised way. However, even this one worked very well for the speech separation task, but it didn't improve the speech enhancement. And then the permutation training here is mean that when you have two sources here, you don't know to assign which label to which source. So that's why they propose a permutation training, so that if you map the clean speech to one or two sources, it's okay. If that is masked a target signal. And then because the mix doesn't improve speech enhancement, so that's why very recently, there a paper that tried to propose a noise augmentation for mix. So what they do is that in the original mix, they only have the signal and the noise recording here, mixing with another noise. So the noise recording here is that the noise already inside the recording, and you don't have the clean speech, but when you record, the noise is already in there. This one contribution that they mentioned, that they try to add the noise here, so that the argument is that when they add the noise there, and then when the noise here has the same distribution as the additional noise here, they expect that the performance of the network will be improved. You can see that I can describe more about some letter here. So the S stands for speech inside the recording, and recording is the noise already inside the recording. So for example, when I record, there's some background noise on the streets. This artificial noise here is that they have some noise data set, and then they try to add the noise to the current recording. And then the noise here is the original noise in the mixed paper. So the order here, I argue that because the noise recording and the noise here have different distribution, so that's why mixed doesn't work. So that's why they try to add the N artificial that have the same distribution at the end, and then they hopefully it work. Based on the current state of the art of unsupervised speech enhancement, we can see some limitation. For example, the mixed it does not have strong constraint to improve speech enhancement. So that's why they don't really improve on speech enhancement data set. And the second paper, augmentation mixed, the test set are not representative because it contains synthetic noisy utterances, and to deploy in real world, we want the test set is more on real world utterances. And then other thing that they haven't discussed is it is a trade-off between speech enhancement and speech recognition. So every time we improve speech enhancement, speech recognition is going worse, and then current state of that haven't addressed that. So that gives us to a proposed solution that we try to utilize the mixed slot for unsupervised training, but we improve it by adding additional constraint. The constraint is that, for example, now we have two outputs. One is speech and one is noise, for example, and then they sum up together to be the noisy mixture. But how we can constrain that the one output is contain more speech and another output contain more noise. So the first thing we can think is that we try to add a disentanglement constraint so that two outputs are different in a specific vector space, and the choice of the vector space will be discussed later in the experiment. So here, for example, we make the dot product of the first output and the second output to be 0. The second one is how to make one output contain more speech information as possible. So in this way, we try to force one output to have similar ASR embedding as a noisy input, because if it contains similar ASR embedding, then we expect that its output will contain speech information. So by adding two constraints, we hopefully make the mix have better performance on speech enhancement. The fourth thing we want to do is that we want to utilize a pre-trained ASR to improve speech recognition and speech enhancement together. So we want to prevent the trade-off. So here is our proposed network architecture. So we have the speech enhancement as normal, but in here we have the input is a noisy mixture, so we don't require clean speech. The input can be any noisy mixture that we record, whether it's from YouTube or it's from Microsoft Teams dataset, or it's from anywhere. And then we have additional noise. This one is noise only recording outside. They combine together in the time domain to become a signal Y here, and come to the input of speech enhancement system. So the speech enhancement system has three outputs. The first one is S, the second one is noise, N1, and the third one is N2. So what we want to do is that we try to make the S contain the speech information. The N1 contain where the noise recording or the additional noise here, and the N2 contain the noise, whether the noise recording, if the N1 contain N, or it contain N when the N1 contain noise recording. So yeah, so one of noise recording or N going to either N1 or N2. Here we also have a pre-trained ASR embedding. So notice that it's not a full ASR. We only need it for the task of extract the embedding for the speech recognition task. And then we take the noisy speech here. We extract the embedding here. And we also take the prediction here and extract the embedding here. So by enforcing the loss here similar to each other, we hope that the speech here will contain the speech information. Yeah, notice that because we don't have a clean speech as a target, so yeah, the signal we have here can be the ASR embedding. And then for N1 and N2, how we encourage contain noise. So the first thing is the disentanglement here, like we make the dot product between N1 and N2 with S is small, so it means that they contain different information with respect to speech. And then we also like, the mix-it loss also constrain it. For example, they try to make the S and N1 combine together to reconstruct the Y here. And then the N2 is similar to the N. So they make the N2 contain N, or whether they make N1 contain N. And our loss function can be the summarization, some of the mix-it loss, the embedding loss, and the disentanglement loss. Here we move to the data set. So the training data set, because we want to compare to the baseline trained on supervised training, so that's why we include the clean data set. Here is the LibVox with 500 hours. We also using the improved response for reverberation augmentation for the supervised baseline. And then we have the noise data set. It is the DNS challenge with 280 hours. And the noise data set, we have Vox select with more than 2,000 hours. We have the development set. It is the DAP out, which is the speak from DAP and the noise from out data set as a citation here. And the test set is the ICAP 2021 blind test set that have the real-world recording with 700 utterances. And the speech recognition, we use a independent speech recognition engine. It is a Microsoft test set, and using the Microsoft Azure ASR. This test set have 3,000 utterances with 25,000 words. So as you can see here, the signal to noise ratio of the LibVox and in blue color and the Vox select. So you can see like a lot of LibVox has signal to noise ratio very high. So that's why we consider it's clean speak. And then many of the Vox select is have low signal to noise ratio, so it is noisy speech. The evaluation metric, we use two kind of evaluation metric. The first one is speech enhancement metric. So we have M6 to measure the signal quality, MBAP to measure the background noise suppression, and M overall is the weight combination between signal and background. Because sometimes when you remove a lot of background noise, then the signal can be have reduced the signal quality. All three courses are from Gen 0 to 5, and then the higher score, the better. And then because the human score is very expensive, so we based on a neural network that trained on the human score level for evaluation. And for speech recognition metric, we just use the standard word error rate, which is lower is better. So here we do an experiment to see whether adding additional noise, like noise augmentation, can help for supervised, unsupervised training. Because the second paper that I discussed, they try to add additional noise. So the input of the network, we have the clean, then have a pre-noise, which is an artificial in the diagram, and then with additional noise here. And the target will be clean and pre-noise because it's unsupervised training. So what we can observe that we see that the signal to noise ratio that have the best performance actually is when we don't have any pre-noise at all, because the signal to noise ratio is 100. So it means that we almost has no noise. So we in contrast with the finding in this paper. And here we also doing that the same. But here we add two noise to the noisy dataset, the Vox select dataset, instead of the clean dataset. So we also observe the same trend, like the higher the signal to noise ratio, the better the performance. So it means that we only need to add one noise instead of two noise. Vì là anh mở đồng hồ also here we also discuss the supervised and unsupervised training results. So the first one, the first experiment is the baseline that we train on a normal loss that often used for speech enhancement. So the input is synthetic noisy by mixing noisy mixtures and the noise. So, and the target in noisy speech, because we don't have the clean speech as target here. And the loss is just a standard traditional supervised loss. This one can be considered as a lower bound for our experiment. And the second one, experiment 2, is that the original mix is. So yeah, the input is the same like noisy speech plus noise. The target is noisy speech, but the loss is the unsupervised make it loss. So we don't use the supervised loss, but we use the unsupervised make it loss. So some observation we can see here. The first, like here is the noisy one. So you can see that the noisy one, the signal is quite good because we don't remove any signal here. So signal score is 3.85, but the background noise is not good because it had a lot of noise here. Then the thing here is that the noisy have good word error rate. And then, as discussed before, every time we add the speech enhancement by removing noise, then you can see that the signal quality is reduced. So from 3.85 to 3.67. Yeah, so when we increase the background noise, reduce the background noise, so the signal increase, background quality increased from 3.32 to 4.01. Then the signal also decreased. So that's why you can see that here the baseline supervised leading to very high word error rate. So it increased from 13.29 to 15.71. And then here we have the result for the original MIG-IT paper. You can see that for the overall, the MIG-IT have the same speech enhancement performance, like the same as the baseline. So that's why in the original paper, they discussed that the speech enhancement using MIG-IT doesn't improve. And then here we also observe the same trend. The reason that the word error rate improved compared to baseline, because I think that they reduce less background noise. So that's why when they reduce less background noise, then the word error rate is better. And then in here is our proposed methods. So the first one, the experiment 3, we do unsupervised training with MIG-IT, but we add an ASR embedding loss constraint. The experiment 4 here, we add the disentanglement constraint on the ASR embed loss. So we have the embed representation for the speech here, and then we have the ASR embedding representation for the noise here, and then we try to make them to be small, so like different signal contain different speech and noise. And then the final one, we combine everything, like compare the we contain everything, like we add the ASR embedding loss and the disentanglement loss. So as we can observe here, our proposed methods improve the speech enhancement. So from 3.33 to 3.36. And then we also do the significant test using the with Gaussian test, and we found that it's significant. And then in here, we also not only improve the speech enhancement, but we also improve the speech recognition. So you can see that the baseline have 15.71, and we reduce the word error rate to 15.07. So it means that we don't have the trade-off between speech recognition and speech enhancement, but we successfully improve on both. And you can see, observe here the contribution on the different loss. So when we add the disentanglement loss, then the M overall improve. So from 3.33 to 3.36. That makes sense because the disentanglement make the signal and the noise go into separate channel. So not only overall, but you see that the background, the background also go from 4.01 to 4.05, and the signal keeping the same. Word error rate for the utterance with low signal to noise ratio also improved, like from 1772 to 732, or for high signal to noise ratio is also improved from 636 to 619, and for the word error rate for the meeting also improved, like 17.83 to 16.95. So it improved on all kind of speech, like low noise speech, high noise speech, and total speech. The disentanglement is not only improve the overall, and then when we add the embedding on the disentanglement, we can see the speech enhancement performance keep the same, and then the error rate is lower down. So the disentanglement helps speech enhancement, and then the ASI embedding help to reduce the word error rate further. So you can see that compared to the disentanglement, it's all reduce the word error rate. Also in here, another thing to notice is that the extra ASI embedding on way to vec2, and it is a pre-trained way to ASR, and then we inference on using the different ASR module. It is the IU ASR. So even we use a different ASR at training and at inference, but the word error rate still reduced. So we can make a conclusion that the proposed methods generalize to new ASR engine. Here we also do an experiment to measure like where should we put the disentanglement. So there are two ways to put the disentanglement. The first one is we put on the spectrogram. So and the second one is we put after the ASR embedding. So I can show the diagram again. Yeah, so there are two ways to enforce the disentanglement. The first one, we try to make the S and the N1 here to be close to each other. And the second one is we put the X here and the S here to be close to each other. Sorry, I mean the first one is we put the S here and the X here close to each other. So the here is the spectrogram, and then this one is embedding after the ASR. So we make the X and the S is similar. So yeah, so we want to measure like which one is better. So we can observe that if we put the disentanglement on spectrogram, then the speech enhancement is not work. You can see the score here very low, like 2.14 only. So even the background is improved compared to noisy like 3.32 to 3.77, but the signal quality degrade a lot from 3.85 to 2.10. So I think the reason is that when we try to put a disentanglement, then the dot product will be small. It means that they try to force maybe one speak is 0 or noisy is 0. So it means that in a single time frequency point in a spectrogram, it makes it contain either speak or noise, but not both. So kind of a binary mass. But it's not it is not reality, because in a high frequency spectrogram, there may be some speak signal there, and there may be some noise signal there. So if we put some kind of like very strict, like in a spectrogram only in one point whether they have speak or noise, then it might work well. But if we put a disentanglement at the ASR embedding level, then it is different, because like it makes like one contain the ASR information and another contain not ASR information. So the one that contain ASR will be speak and another don't contain ASR will be noise. So that's why you can see that the disentanglement on ASR embedding have much better score, like improve the speak enhancement. We also do some semi-supervised training by adding a supervised loss on reverb and unsupervised loss on vox select in a batch. So we can observe that the word error rate total is reduced, and then the speak enhancement score is similar to the supervised. So because this one is still on training, so we expected that we have a better result when it finished training. And yeah, we can see that even we train on a supervised, like we have a clean dataset at target, it has still have higher word error rate on than the unsupervised. This one is unsupervised exponent 5. We only using noisy dataset, and then the word error rate is still lower than the one training on supervised. But the one training on supervised is better, because it train on both. It can train to reduce the reverberation and the noise. While in the unsupervised way, we haven't found a way to remove the reverberation. So that's why you can see that the speak enhancement score is better. But compared to the one for a fair comparison with supervised one that have the target a clean and reverberation, we are quite close, like 3.36 and 3.41, and have much better word error rate. And also here, I can play some example noisy dataset. So here you can see the noisy input.
The structures housing the apartments are of masonry and frame construction. First, they wanted to clarify a tantalizing, bizarre enigma. Why charge money for such garbage? In developing film, many toxic chemicals are used. You had to be stupid or crazy or immortal.
Yeah, so you can see that there speak information there, and then there's some background noise, for example, the baby crying. And here you can hear the baseline speech.
The structures housing the apartments are of masonry and frame construction. First, they wanted to clarify a tantalizing, bizarre enigma. Why charge money for such garbage? In developing film, many toxic chemicals are used. You had to be stupid or crazy or immortal.
Yeah, you can see that they remove some background noise, the baby crying, but the speak has some distortion. And here the proposed methods.
The structures housing the apartments are of masonry and frame construction. First, they wanted to clarify a tantalizing, bizarre enigma. Why charge money for such garbage? In developing film, many toxic chemicals are used. You had to be stupid or crazy or immortal.
Yeah, so you can see that the background noise is removed and then there are less distortion than the baseline. I think there are still some distortion, but yeah, but it had to remove everything.
The structures housing the apartments are of masonry and frame.
Yeah, so it leads to our conclusion is that the original mix is lost, do not improve the speed enhancement, and then the proper methods that we add additional constraint by utilize the ASR embedding, and then the disentanglement loss improve both speed enhancement and speed recognition. So we can see that there are no trade-off here between speed recognition and speed enhancement. And then the proper method generalized to new ASR engine at inference time. The disentanglement at ASR embedding representation had a better performance than at spectrogram representation. So I think this can be a contribution for kind of research, because I see that a lot of people, they are doing the disentanglement or orthogonality at the spectrogram level. And then another thing is that any real-world noisy speed corpora could be utilized to improve speed enhancement by combining supervised and semi-supervised approaches. Another thing to notice that because of the timeline of the project, we use a small speed enhancement. So if we can use a bigger speed enhancement model in our dataset, we can much further improve the speed enhancement quality and then the speed recognition quality. So all the report here can be improved if we use a bigger model. And some future work, like to mitigate the speed enhancement and speed recognition trade-off, we can do some thing like we try to maintaining important speed queue for SR when doing speed enhancement. So I have some research on this topic to finding the important speed queue, and hopefully that in future I can apply the PhD research topic in the university in the topic of speed enhancement to make both of them work together. So it's not only apply to speed recognition, but it can apply to speed emotion or speaker recognition by maintaining some important speed queue when we doing speed enhancement for that topic. The second thing is that the current work we do the peer permutation, so that's why it takes a lot of training time. And then there's a current paper, they use the Hungary algorithm to optimize the permutation problem. Yeah, by using this, we can optimize the permutation computation a lot for both speed enhancement and speed separation. Another trend of future work can be like semi-supervised training, and then we also can do contrastive learning for speed enhancement. Yeah, so this is the end of my talk. I would like to thank Sebastian for his mentor and guidance, audio acoustic group, and Deependra Mitra in the reinforcement learning group for the useful feedback and suggestion on the project. Also, I want to thank you, Human Centered AI, for the interesting summer intern talk series, and our group, the IC3, IC3 AI, ASZ, MSRA, and coordination group for the beneficial and useful machine learning speed enhancement workshop. Thank you, and I hope to hear some feedback and questions from you.
Yeah, thank you. Great talk, yet. Any questions from the audience? We have some time left. Unfortunately, the noise, the background noise from your microphone was still audible over the noise samples you played.
Yeah.
But I think the difference was audible. No questions. So then I'll start off with one question. So on this disentanglement loss term that you used, so this basically tries to make two representations dissimilar, right?
Yes.
Or similar.
We try to make it dissimilar because we make the dot product to be 0. But the disentanglement here is on the abstract space. So yeah, it's not on spectrogram signal space, but for the ASI, it's kind of abstract. So we observe that by more abstract representation, disentanglement in the abstract representation is better than the original spectrogram representation.
Okay, so but you haven't tried. So you tried to for the spectral disentanglement. So I'm wondering why this did not work. So you tried to make the speech and the noise outputs different, right? Or something else?
Yeah, the speak and the noise different, yeah.
Okay.
Yeah, because I mentioned like, because if we make it in spectrogram space, then it means that similar and for the binary mass in spectrogram, like one single time frequency point can contain only speak or noise. But it's not a realistic because in reality, in one single time, we can have like two speakers or speak and noise at the same time, right? At a single frequency being. So that's why I think that's why it didn't work.
Mm-hmm.
I have a question, Viet, Sebastian. In the mixed loss that you have on the second line, I see that you're both forcing your N1 to go close to the recording noise and or also go closer to the other type of noise, the additive noise.
Yes.
Is there a reason why you're trying to do both at the same time?
I mean that for the original one, this is the original loss function, but I don't see any constraint that push S to contain speech. So they only constrain noise, the N to similar to noise. But I don't see anything that puts the S here, the S predict S, close to the speech, right? But I think it is really important because if we don't constrain on S, then we constrain on noise, then maybe it's not enough, not strong enough. Then how we can constrain on S? So for supervised training, we have the clean speech target. So that's why we can easily constrain on the speech. Like we just make the output of the network similar to clean speech. But the question here is when we don't have the clean speech as target, how we can constrain it. So that's why we use the ASI embedding to make the, because the ASI embedding pre-trained is very robust to noise. So we expected that the embedding, ASI embedding of the noisy speech and the clean speech is similar. So even we don't have the clean speech, but we have the embedding, ASI embedding of a noisy speech, and we know that it's similar to the clean, and then we can use that to make the constraint on the S. Yeah, so that is different.
Isn't that confusing a little bit, the loss function, if you're trying to push N1, if you're trying to push for example, on your mixed loss down here on the line, you're trying to push the noise N to be close to the embedding at N1, but also N2 to be close to N.
Oh yeah, it is a permutation loss. So it is yeah, permutation loss, like we the minimum here. So because we don't know.
It's an either or.
Okay.
So basically, it's you try both combinations and you take the one that has the lower loss. So that's why there's this min operation.
Got it.
So this idea is basically from the permutation invariant loss, which is very popular in source separation. So basically try to separate two sources, but you do this permutation, so you actually don't know in which output your both sources end up, right? But you at least enforce that always the same source goes to the same output, so that they keep consistent over time. That's kind of the idea of this.
So do you let the first couple of epochs decide that, and then you stick with whichever permutation made sense?
No, it's just per utterance or per training sequence, basically. So it basically tries to enforce consistency over time, that always the same source over time goes to the same output.
Got it. Thank you.
All right. Any other questions?
How big is the model?
Yeah, in here we use the smallest one, so I think it's around 2 million parameter. Very small, yeah.
It was Cruise 16.
So
more or less.
In your future, you plan to have a really large model like maybe Cruise 64 or something, and then use that as a teacher to train the smaller models? Is that one possibility?
No, it's kind of it can be used for any model. It's just it would enable you to utilize noisy speech recordings for basically. Then hopefully by just adding much more data to your training, you might be able to improve actually over the just using the supervised training data that we have.
Right, but the SIG is still lower than noisy, right, in your final results. So do you hope that with the larger model that gap will get bridged?
Yes, it should.
A lot more data set and bigger model?
Yeah.
Okay.
So basically, you get this one baseline, which is just traditional supervised training, like as everyone does. And he could show like over this baseline, there seems to be a little improvement with this unsupervised or semi-supervised training at least.
Yeah.
Right. 1 minute left. Last chance for questions. Otherwise, I guess we thank Viet again. Very nice presentation. Thank you all for attending.
Thank you, Viet.
Yeah. And I will stop the recording now.
Yeah. Thank you, everyone.